Up until this point, all of our motion has been linear, straight line. Now we're going to start to examine circular motion. Objective: circular motion. Describe the two types of circular motion. Describe the relationship among tangential speed, rotational speed, and radial distance. Describe the factors that affect the centripetal force acting on an object. Explain the centrifugal force effect. Explain why centrifugal force is not considered a true force. The big idea: centripetal force keeps an object in circular motion, which moves faster on a merry-go-round, a horse near the outside rail or one near the inside rail. If you swing a tin can at the end of a string in a circle over your head and the string breaks, does the can fly directly outward, or does it continue its motion without changing its direction? While a hamster rotates its cage about an axis, does the hamster rotate or does it revolve around the same axis? These questions indicate the flavor of this chapter. We begin by discussing the difference between rotation and revolution. Rotation and revolution. Why do objects move in circles? Roll a marble around the rim of a paper plate. Using a pair of scissors, cut a 90-degree wedge-shaped piece from the plate. Roll the marble around the rim of the modified plate. Analyze and conclude. Observing. Describe the motion of the marble before and after a section of the plate was removed. Predicting. What could you do to keep the marble moving in a circle? Making generalizations. What is required to keep any object moving in a circle? 10.1. Rotation and revolution. Both the Ferris wheel shown in figure 10.1 and an ice skater doing a pirouette turn around an axis. An axis is a straight line around which rotation takes place. You rotate about an internal axis when you spin. You revolve around an external axis when you circle about that axis. Two types of circular motion are rotation and revolution. When an object turns about an internal axis, that is, an axis located within the body of the object, the motion is called rotation or spin. Both the Ferris wheel and the skater rotate. Figure 10.1, the Ferris wheel turns about an axis. When an object turns about an external axis, the motion is called revolution. Although the Ferris wheel rotates, the riders revolve around its axis. Earth undergoes both types of rotational motion. It revolves around the sun once every 365 1/4 days, and it rotates around an axis passing through its geographical poles once every 24 hours. Notes: you rotate about an internal axis when you spin. You revolve around an external axis when you circle about that axis. Concept check. What are two types of circular motion? A point to consider. Let's continue with a think. At an amusement park, you and a friend sit on a large rotating disc. You sit at the edge and have a rotational speed of 4 revolutions per minute. or RPMs, and a linear speed of 6 meters per second. Your friend sits halfway to the center. What is her rotational speed? What is her linear speed? Her rotational speed is 4 RPM, and her linear speed is 3 meters per second. 10.2 Rotational Speed. We begin this chapter by asking which moves faster on a merry-go-round, a horse near the outside rail or one near the inside rail. Similarly, which part of a turntable moves faster on a pre-CD record player shown in figure 10.2. Which part of the record moves faster under the stylus? The outer part where the ladybug sits, or a part near the orange center? If you ask people these questions, you'll probably get more than one answer because some people will think about linear speed while others will think about rotational speed. Figure 10.2. The turntable rotates around its axis while a ladybug sitting at its edge revolves around the same axis. Consider this very carefully. Types of speed. Linear speed, which we simply called speed in Chapter 4, is the distance traveled per unit time. A point on the outer edge of a merry-go-round, or a turntable travels a greater distance in one complete rotation than a point near the center. So the linear speed is greater on the outer edge of the rotating object than it is closer to the axis. The speed of something moving along a circular path can be called tangential speed because the direction of motion is always tangent to the circle. For circular motion, we can use the terms linear speed and tangential speed interchangeably. Rotational speed, sometimes called angular speed, is the number of rotations per unit of time. All parts of the rigid merry-go-round and the turntable rotate about their axis in the same amount of time. Thus, all parts have the same rate of rotation or the same number of rotations per unit time. It is common to express rotational speed in revolutions per minute, RPM. For example, phonograph turntables that were common in the past rotate at 33 1/3 RPM. A ladybug sitting anywhere on the surface of the turntable in figure 10.3 revolves at 33 1/3 RPM. Tangential and rotational speed. Tangential speed and rotational speed are related. Have you ever ridden on a giant rotating platform in an amusement park? When I was a kid, we used to buy record single songs, and they were 45 RPMs. All parts of the turntable rotate at the same rotational speed. A point farther away from the center travels a longer path in the same time and therefore has a greater tangential speed. B. A ladybug sitting twice as far from the center moves twice as fast. Think. Train wheels ride on a pair of tracks. For straight line motion, both tracks are the same length, but which track is longer for a curve? The one on the outside or the one on the inside of the curve? Similar to figure 10.3, the outer track is longer, just as a circle with a greater radius has a greater circumference. The faster it turns, the faster your tangential speed is. Tangential speed is directly proportional to the rotational speed and the radial distance from the axis of rotation. So we state tangential speed is proportional to radial distance times rotational speed. In the symbol form, V equals R omega, where V is tangential speed and omega, is rotational speed. You move faster if the rate of rotation increases. That's a bigger omega. Omega is the last of the Greek letters. A to Z, well, omega is the last letter. It's alpha to omega. How does linear speed depend on radius? Roll a cylinder can across a table. Note the path the rolling can takes. Now, roll an ordinary tapered drinking cup on the table. Does the cup roll straight or does it curve? Does the wide end of the cup cover more distance as it rotates? Think. Is the linear speed of the wide end of the tapered cup greater than the linear speed of the narrow end? I point to ponder. You also move faster if you are farther from the axis, bigger R. At the axis of a rotating platform, you have no tangential speed, but you do have rotational speed. You rotate in one place. As you move away from the center, your tangential speed increases while your rotational speed stays the same. Move out twice as far from the center, and you have twice the tangential speed. This is true for the ladybugs in figure 10.3. Move out 3 times as far, and you have 3 times as much tangential speed. To summarize, in any rigid rotating system, all parts have the same rotational speed. However, the linear or tangential speed can vary. Tangential speed depends on rotational speed and the distance from the axis of rotation. Railroad train wheels. Why does a moving freight train stay on the tracks? Most people assume that flanges on the edges of the wheels prevent the wheels from rolling off the tracks. However, these flanges are only in use in emergency situations or when they follow slots that switch the train from one set of tracks to another. So how do the wheels of a train stay on the track? They stay on the track because their rims are slightly tapered. A curved path occurs when a tapered cup rolls, as shown in figure 10.4. The wider part of the cup travels a greater distance per revolution. As illustrated in figure 10.5, if you fasten a pair of cups together at their wide ends and roll the pair along a pair of parallel tracks, the cups will remain on the track and center themselves whenever they roll off center. This occurs because when the pair rolls to the left of center, for example, the wider part of the left cup rides on the left track while the narrow part of the right cup rides on the right track. This steers the pair toward the center. If it overshoots toward the right, the process repeats, this time towards the left, as the wheels tend to center themselves. Figure 10.4, a tapered cup rolls in a curve because the wide part of the cup rolls faster than the narrow parts. Figure 10.5, a pair of cups fastened together will stay on tracks as they roll. The wheels of railroad trains are similarly tapered, as shown in figure 10.6. This tapered shape is essential on the curves of railroad tracks. On any curve, the distance along the outer part is longer than the distance along the inner part, as illustrated in figure 10.3a. So whenever a vehicle follows a curve, its outer wheel travels farther than its inner wheel. For an automobile, this is no problem because the wheels roll independent of each other. For a train, however, pairs of wheels are firmly connected like the pair of fastened cups, so they rotate together. Opposite wheels have the same RPM at any time. Figure 10.6, the tapered shape of railroad train wheels, shown exaggerated here, is essential in the curves of railroad tracks. But due to the slightly tapered rim of the wheel, when a train rounds a curve, wheels on the outer track ride on the wider part of the tapered rim and cover a greater distance in the same time, while opposite wheels ride on their narrower parts, covering a smaller distance in the same time. This is illustrated in figure 10.7. In this way, the wheels have different linear speeds for the same rotational speed. Figure 10.7. When a train rounds a curve, the wheels have different linear speeds for the same rotational speed. A. Narrow part of left wheels goes slower, so wheels curve to the left. B. Wide part of the left wheel goes faster, so wheels curve to the right. This is V equals R omega in action. Can you see that if the wheels were not tapered, scraping would occur and the wheels would squeal when a train rounded a curve on the tracks? Concept check. What factors affect the centripetal force acting on an object? 10.3 Centripetal force. Velocity involves both speed and direction. When an object moves in a circle, even at constant speed, the object still undergoes an acceleration because its direction is changing. This change in direction is due to a net force. Otherwise, the object would continue to go in a straight line. Any object moving in a circle undergoes an acceleration that is directed to the center of the circle, a centripetal acceleration. Centripetal means toward the center. Correspondingly, the force directed toward the fixed center that causes an object to follow a circular path is called a centripetal force. The force you feel from the wall while on rotating Carnival centrifuge is a centripetal force. It forces you into a circular path. If it ceased to act, you'd move in a straight line in accord with the law of inertia. Examples of centripetal forces. If you whirl a tin can on the end of a string, as shown in figure 10.8, you find you must keep pulling on the string, exerting a centripetal force. The string transmits the centripetal force, pulling the can from a straight line path into a circular path. Centripetal forces can be exerted in a variety of ways. The string that holds the moon on its almost circular path, for example, is gravity. Electrical forces provide the centripetal force acting between an orbiting electron and the atomic nucleus of an atom. Figure 10.8, the force exerted on a whirling can is towards the center. No outward force acts on the can. Anything that moves in a circular path is acted on by a centripetal force. Centripetal force is not a basic force of nature, but is simply the label given to any force, whether string tension, gravitation, electrical force, or whatever that is directed toward a fixed center. If the motion is circular and executed at constant speed, this force acts at right angles, perpendicular to the path of the moving object. When an automobile rounds a corner, for example, friction between the tires and the road provide the centripetal force that holds the car in a curved path. This is illustrated in figure 10.9a. If friction is insufficient due to an oily surface, gravel, etc., the tires slide sideways and the car fails to make the curve. Figure 10.9. Centripetal force holds a car in a curved path, A. For the car to go around the curve, there must be sufficient friction to provide the required centripetal force. If the force of friction is not great enough, skidding occurs. As shown in figure 10.9b, the car tends to skid tangentially off the road. Centripetal force plays the main role in the operation of a centrifuge, which you may use in biology lab to separate particles in a liquid. A household example is the spinning tub in an automatic washer, like the one shown in figure 10.10. In its spin cycle, the tub rotates at high speed, and the tub wall produces a centripetal force on the wet clothes, forcing them into a circular path. The holes in the tub's wall prevent the tub from exerting the same force on the water in the clothes. The water escapes tangentially out the holes. Strictly speaking, the clothes are forced away from the water. The water is not forced away from the clothes. Think about that. Figure 10.10, the clothes in a washing machine are forced into a circular path, but the water is not, and it flies off tangentially. Calculating centripetal forces. The centripetal force on an object depends on the object's tangential speed, its mass, and the radius of the circular path. Greater speed and greater mass require greater centripetal force. Traveling in a circular path with smaller radius of curvature requires a greater centripetal force. In the equation, centripetal force equals mass times speed squared divided by the radius. Centripetal force Fc is measured in newtons, where m is expressed in kilograms, v in meters per second, and r in meters. Adding force vectors. Figure 10.11 is a sketch of a conical pendulum, a bob held in a circular path by a string attached above. This arrangement is called a conical pendulum because the string sweeps out a cone. Figure 10.11. The string of a conical pendulum sweeps out a cone. Only two forces act on the bob: mg, the force due to gravity, and tension T in the string. Both are vectors. Figure 10.12 shows vector T resolved into two perpendicular components, Tx horizontal and Ty vertical. We show these vectors as dashed to distinguish them from the tension vector T. Interestingly, if vector T were replaced with vectors represented by these component vectors, the bob would behave just as it does when it is supported only by T. Recall from Chapter 5 that resolving a vector into components is the reverse of finding the resultant of a pair of vectors. More on resolving vectors in Appendix D and in the Concept Development Practice Book. Figure 10.12, the vector T can be resolved into a horizontal Tx component and a vertical Ty component. Since the bob doesn't accelerate vertically, the net force in the vertical direction is 0. Therefore, the component Ty must be equal and opposite to mg. What do we know about component Tx? That's the net force on the bob. The centripetal force. Its magnitude is mb over r squared, where r is the radius of the circular path. Note that centripetal force lies along the radius of the circle swept out. As another example, consider a vehicle rounding a banked curve, as illustrated in figure 10.13. Suppose its speed is such that the vehicle has no tendency to slide down the curve or up the curve. At that speed, friction plays no role in keeping the vehicle on the track. Interestingly, the angle of the banked curves are chosen for 0 friction at the designated speed. Figure 10.13. Centripetal force keeps the vehicle in a circular path as it rounds a banked curve. Only 2 forces act on the vehicle. One, mg, and the other, the normal force, n, the support force of the surface. Note that n is resolved into nx and ny components. Again, ny is equal and opposite to mg, and nx is the centripetal force that keeps the vehicle in a circular path. Whenever you want to identify the centripetal force that acts on a circularly moving object, it will be the net force that acts exactly along the radial direction toward the center of the circular path. Concept check. What factors affect the centripetal force acting on an object? Mixtures are separated in a centrifuge according to their densities. That's how cream is separated from milk, and lighter plasma is separated from heavier blood corpuscles. 10.4 Centripetal and centrifugal forces. In the preceding example, circular motion is described as being caused by a center-directed force. Sometimes an outward force is also attributed to circular motion. This apparent outward force on a rotating or revolving body is called centrifugal force. Centrifugal means center fleeing or away from the center. In the case of the whirling can, it is a common misconception to state that centrifugal force pulls outward on the can. If the string holding the whirling can breaks, as shown in figure 10.14, it is often wrongly stated that centrifugal force pulls the can from its circular path. Figure 10.14, when the string breaks, the whirling can moves in a straight line, tangent to, not outward from, the center of its circular path. But in fact, when the string breaks, the can goes off in a tangential straight line path because no force acts on it. We illustrate this further with another example. Suppose you are the passenger in a car that suddenly stops short. If you're not wearing a seatbelt, you pinch forward toward the dashboard. When this happens, you don't say that something forced you forward. You know that you pinched forward because of the absence of a force, which a seatbelt provides. Similarly, if you are in a car that rounds a sharp corner to the left, you tend to pinch outward against the right door. Why? Not because of some outward or centrifugal force, but rather because there is a centripetal force holding you in circular motion. The idea that centrifugal force bangs you against the car door is a misconception. Why doesn't the water fall out of the bucket? Fill a bucket halfway with water. Swing the bucket of water in a vertical, circular, fast enough that the water won't fall out at the top. Think, why does the water stay in the bucket? Something to ponder. So when you swing a tin can in a circular path as shown in figure 1015, there is no force pulling the can outward. Only the force from the string acts on the can to pull the can inward. The outward force is on the string, not on the can. Now suppose there is a ladybug inside the whirling can as shown in figure 1016. The can presses against the bug's feet and provides centripetal force that holds it in a circular path. The ladybug in turn presses against the floor of the can. Neglecting gravity, the only force exerted on the ladybug is the force of the can on its feet. Notes: if you bang against the door, action. The door bangs against you, reaction. Figure 1015, the only force that is exerted on the whirling can, neglecting gravity, is directed towards the center of the circular motion. This is centripetal force. No outward force acts on the can. Very important illustration. So is the next one. Figure 1016, the can provides the centripetal force necessary to hold the ladybug in a circular path. From our outside stationary frame of reference, we see there is no centrifugal force exerted on the ladybug. The centrifugal force effect is attributed not to any real force, but to inertia, the tendency of the moving body to follow a straight line path. What causes the centrifugal force effect? Careful consideration. 10.5, centrifugal force in a rotating reference frame. Our view of nature depends on the frame of reference from which we view it. For instance, when sitting in a fast-moving vehicle, we have no speed at all relative to the vehicle, but we have an appreciable speed relative to the reference frame of the stationary ground object. From one frame of reference, we have speed. From another, we have none. Likewise with force. Recall the ladybug inside the whirling can. From a stationary frame of reference outside the whirling can, we see there is no centrifugal force acting on the ladybug inside the whirling can. However, we do see centrifugal force acting on the can and the ladybug producing circular motion. But nature seen from the reference frame of rotating system is different. In a rotating frame of reference of the whirling can shown in figure 1017, both centripetal force supplied by the can and centrifugal force act on the ladybug. To the ladybug, the centrifugal force appears as a force in its own right, as real as the pull of gravity. However, if she were to stop rotating, she would feel no such force. Thus, there is a fundamental difference between the gravity-like centrifugal force and actual gravitational force. Gravitational force is always an interaction between one mass and another. The gravity we feel is due to the interaction between our mass and the mass of Earth. However, in a rotating reference frame, the centrifugal force has no agent such as mass. There is no interaction counterpart. Figure 1017, from the reference frame of the ladybug inside the whirling can, the ladybug feels as if she is being held to the bottom of the can by a force that is directly away from the center of circular motion. Centrifugal force is an effect of rotation. It is not part of an interaction, and therefore it cannot be a true force. For this reason, physicists refer to centrifugal force as a fictitious force, unlike gravitational, electromagnetic, and nuclear forces. Nonetheless, to observers who are in a rotating system, centrifugal force is very real, just as gravity is ever present on Earth's surface. Centrifugal force is ever present within a rotating system. Why is centrifugal force not considered a true force? A heavy iron ball is attached by a spring to a rotating platform as shown in the sketch. Two observers, one in the rotating frame and one on ground at rest, observe its motion. Which observer sees the ball being pulled outward, stretching the spring? Which observer sees the spring pulling the ball into a circular motion? The observer in the reference frame of the rotating platform states that centrifugal force pulls radially outward on the ball, which stretches the spring. The observer in the rest frame states that centripetal force supplied by the stretched spring pulls the ball into circular motion. Only the observer in the rest frame can identify an action-reaction pair of forces, where action is spring on ball, reaction is ball on spring. The rotating observer can't identify a reaction counterpart to the centrifugal force because there isn't any. Since 1884, when the first American roller coaster was constructed, roller coasters have evolved into thrilling machines that rise over 100 meters high and reach speeds of 150 kilometers per hour. Roller coaster designers, or mechanical design engineers, use the law of physics to create rides that are both exciting and safe. In particular, designers must understand how roller coasters can safely navigate tall loops without exerting too much force on the riders. Designers of modern roller coasters first test their designs on computers to identify any problems before construction begins. Many private companies design roller coasters for amusement parks throughout the world. Circular motion summary. Two types of circular motion are rotation and revolution. Rotation and revolution. Tangential speed depends on rotational speed and the distance from the axis of rotation. The centripetal force on an object depends on the object's tangential speed, its mass, and the radius of its circular path. The centrifugal force effect is attributed not to any real force, but to inertia, the tendency of a moving body to follow a straight line path. Centrifugal force is an effect of rotation. It is not part of an interaction, and therefore it cannot be a true force.